Good afternoon, everybody. I'm Katherine Blundell, Gresham Professor of Astronomy. And the title of my talk this afternoon is Attentive Eyes. I'm going to be talking about what we humans can see in the night sky and what some of it means. So I'm going to be starting with this beautiful picture taken through some Australian eucalyptus trees by my friend and colleague Stephen Lee. You can see right in the center a slender crescent moon, the rest of the moon being illuminated very, very faintly by Earth's shine. The crescent bit of the moon, of course, is illuminated by the sun. What else can we see in this picture besides eucalyptus trees? Well, we can see Jupiter up close near the moon, and hiding in the trees, we can see Mercury. It's a delight to study the pattern and passage of planets through the night sky. And these are some delightful examples, Mercury and Jupiter, but I want to talk a little more today about Mars. While this is a very beautiful conjunction meaning the appearance together of particular planets in the night sky, I want to talk about Mars on its own, what we can see and what we can learn about the planet Mars, the famous red planet, the fourth planet out from the sun. It's got a very thin atmosphere, but interestingly, days and seasons are very comparable to those of Earth because its rotational axis and the orientation of that axis are very similar to those of planet Earth. A year on Mars is getting on for twice that of Earth's. So by astrophysical standards, that's pretty comparable. So how do we go about looking at Mars, and what can we actually see when we point a telescope at it? Well, pointing a telescope at Mars is exactly what I did on Monday night, which those of you living in the UK may recall was a very humid night. We'd had a huge amount of rain before the weekend. It's not at all easy observing something that's fairly low towards the horizon, so is looking through a lot of atmosphere above houses that are giving off heat and causing their own turbulence and unsettlement to the atmosphere itself. So a standard technique, if you want to look at Mars, is to take a whole movie, a whole sequence of images, and then pull out the best. This technique is formally known as lucky imaging. And so if I show you from this entire movie sequence some of the best ones, I hope you'll agree that they are distinctly better than some of the fuzzy ones we saw while the movie was actually bobbing around. So this is a rather nice one. You can just about, I hope, get a sense of the slightly different coloured rock on the planet Mars, slightly greyer towards the bottom left, slightly more muted apricot towards the top right. In the bottom left corner, not that a planet has corners, I hasten to add, but at approximately the 8 o'clock position, you can see some whiter light, and that's actually coming from the ice caps that are on the south pole of Mars. Well, here's another still taken from that blurry, bouncy, bobbly movie I was showing you earlier, and another one still. And I hope you get a sense that these features on Mars are actually rotating as we look throughout time. So these movies were taken during the course of perhaps a couple of hours on Monday evening, and these are the best ones that were pulled out. Now, an astronomer called Rob Tilsley has turned this into an art form, and with an immense tour de force, he has made 77 separate videos of Mars, 924,000 frames between them, and he's pulled out the best 1,300,000 or so, and he has been able to get an entire rotational period of Mars. And this shows you, I think, that you really can see these features propagating around on Mars, despite the limitations of observing during not tremendous weather from the UK. Now, the details of the surface structure of Mars have been the source of some controversy and indeed confusion in past years and the past century or two. So the Turkish astronomer Antonaldi, who was a highly reputed observer, in many ways a very skilled empirical astronomer, for a while supported the notion of canals on Mars. This was until he used a larger, better telescope at the Meudon Observatory, which is south of Paris, and a telescope that has made many important discoveries in the history of astronomy. The main proponent of the idea of canals on the planet Mars was Schiaparelli, the Italian astronomer. Now, he reported observations of seas and canali on the surface of Mars. Now, canali actually means channels, but it was taken to mean canals. The significance of the difference between canals and channels is that canals are artificial, they're made by humans, whereas channels, one can imagine those being formed by the various geological processes in the formation of the planet. However, the idea of canals on Mars was popularized, and folklore about intelligent life on Mars abounded. Fake news is not new, it would seem. Well, the American businessman turned astronomer Percival Lowell, who founded the Lowell Observatory in Arizona, devoted his astronomical endeavors to searching for evidence of intelligent life on Mars. But after his death in 1916, when there was no longer a living proponent for the existence of the canals and therefore the existence of intelligent life on Mars, the consensus of opinion really turned against it. But I think we can have a sense of how that idea grew up because we know that eyes can play tricks on us. We know that optical illusions can confuse the brain. Let me show you an example of that. So just a kilometre or two away from where this lecture here in Bernard's Inn is coming to you from is St. Paul's Cathedral. If we imagine the moon high in the sky above that, we see it as a very big object, subtending quite a large angle in our view of the landscape. If the moon is a lot closer, then a great many folk report that the lower down moon is rather smaller than the moon that's at the top of this photograph. In fact, these two images of the moon are absolutely identical in angular size. But because when we look at the sky, we're not just dealing with our eyes as inanimate detectors, we also very much involve the brain, which sometimes helpfully, sometimes unhelpfully, puts its own interpretation on what we see, then there is scope for humans to get a little bit confused. Well, for a really definitive answer of what the surface landscape is like on Mars, you can't beat a satellite, ideally one costing $1 billion to give you a good picture of what's going on. So this is NASA's Viking orbiter, and it has revealed that Mars has craters, just like on the moon, although fewer of them, because Mars does have an atmosphere, albeit a rather thinner atmosphere than the one on the moon. The Viking orbiter found quite a lot of evidence of geological forms, including volcanic activity, or at least past volcanic activity. It also confirmed the idea that the polar caps, again we're seeing the South Pole here, very much capture ice, water in the form of its solid form of ice. So $1 billion certainly gets you some pretty impressive images from another planet in our solar system, another rocky planet. But I'm going to show you next an image from the ground, from Australia, which is approaching the kind of state-of-the-art image that you can indeed hope to get of this particular planet. So it's very rewarding to get to know Mars and to study it as it rotates and as it moves through the sky. But Mars is a rather bright planet. Relative to some of the other things that I'm going to be talking about, it's very bright indeed in the night sky. It's one of the brightest things that we can look at after Jupiter and so on, of course. But how do we look at fainter things in the night sky? Specifically, how do we go about seeing in the dark? Well, when you first go outside on a dark, clear night, free of clouds, free of raindrops, even if it's beautifully dark and the sun has long set, you probably won't see a thing straight away. And that's because you're not dark adapted. But if you stand for a few minutes, then sooner or later it becomes possible to discern different objects in the night sky. It can take a while. It's usually better to look at the night sky when the moon isn't there, unless you want to study the moon itself, because we get a huge amount of light from the moon. The moon reflects something like 7% of the light that is incident upon it from the sun. The moon itself is a big lump of coal, a spherical lump of coal. But by the time you're squirting a lot of sunlight at it, and we know the sun is dangerously bright, when you reflect 7% of that light, it's still very bright indeed. So you may just be able to make out at the top of the image, Venus, and then further down to the right, Jupiter. It takes a while to be able to see things in the night sky, even when it's clear, even when it's dark. And that's for two reasons. The process of dark adaptation, which is the means by which humans can see things at night, is for two reasons. So the first crucial ingredient about getting dark adapted is time. You need to allow time. You need to give yourself time before your eyes will re-engage gear from being adapted for your modern household, presumably with electric lights and all that kind of good stuff. You need to allow time to get dark adapted in two ways. The first of which is your pupils need to dilate. When light levels are low, then pupils typically dilate, acquire a larger diameter to let more light in and to see fainter things because they can collect more light, because they have a larger aperture. This typically doesn't take too long. I'm talking a few minutes or so, perhaps even in an extreme case. But the bit that takes a long time, but that gives you the most advantage, is when something called rhodopsin kicks in to our retina and plays its role. This is something that massively increases the sensitivity of our retinas to very low intensity light. This cannot be rushed. You really do need to wait 30 or 40 minutes if you want to look and see things in the night sky in order to feel the full effect. But the rhodopsin in our retinas is amazing. It can increase what we can see by a very significant amount indeed, if we allow time for that process to take place. But there's a second thing that we can do to massively increase what we can see in the night sky, and that is to use averted vision. So we don't want to use direct vision here, we want to use averted vision. Why am I saying this? Well, the eye has two different types of detectors, two different types of cells. So the first one of these that I'm going to describe are the so-called cones. So the cone cells in our eyes are the cells that are responsible for colour vision. They can be sensitive, for those of us blessed with good eyesight, in the red or the green or the blue. Collectively, those signals then get synthesized together by our brains into a colour image. These are the cells that are working for us, delivering images to our brains, if we are looking at something straight on. However, the second type of cells in our eyes are known as rods. There are vastly more rods throughout our retinas in the periphery of the light-receiving surface outside of the main density of the cones. Now, the amazing thing about rods is that they are sensitive to very low light sensitivity, very low light levels indeed. There are a lot of them. And if you have a lot of detectors, even if you're only getting one photon here, one photon here, if all of those detectors are feeding the signal to the brain, then you end up being able to see a whole lot more if you use averted vision. What do I mean by averted vision? Simply that you look off axis by about 10, 12, 15 degrees, something like that. So you're no longer looking directly along the line of sight to the astronomical object of interest. If you look off axis a bit, then the light from the astronomical object of interest lands on the rods, those cells that are really sensitive to low intensity of light. And you really want to be able to do that because when you look with averted vision rather than with direct vision, your eyes can then be 40 times more sensitive than direct vision. But again, you need to allow that half an hour at the start of observing. So what sort of things can you see in the night sky? Well, even in July, when in the UK it doesn't get astronomically dark, you could see some beautiful sights. And one such sight many of us were lucky enough to be able to see was comet Neowise, shown here in all its colourful splendour. Now, if you could do an amusing experiment with the comet. If you looked at it in direct vision, you could see it was there and it had a bit of a tail going upwards. If you then looked with averted vision, the tail became about 4 times longer. So it was a fun object on which to practice using your averted vision. Of course, the image that I'm showing you here, I took with my DSLR camera, my digital camera. And I'm now here going to show you a different kind of lucky imaging. If I zoom in even further, while I was totally focusing on the beautiful comet Neowise, in this 4-second exposure, I was lucky enough to capture the meteor that you see heading off towards 10 o'clock. I could not have planned that. I could never repeat it. This is an unusual kind of lucky imaging. So averted vision is how you see more in the night sky. So what might we be able to see in the night sky in the coming months? Well, we're getting to the time of year where Orion and the Pleiades that I discussed in quite some detail in my 6th Gresham lecture in May, the one called Perceptions, Expectations and Discoveries. And at this time of year, or as we go more towards the end of the calendar year, we can see the beautiful constellation of Orion, named after the hunter. We can see the very bright star Aldebaran, and we can also see the Pleiades. These, remember, are that group of stars that always characterize the last few months of the calendar year, and in the southern hemisphere, they are a signal that it's time to start growing crops for the spring. This is a very important sign in Latin America, for example. So I'm going to show you now a beautiful image of the Orion constellation. This one is taken by Will Gatter. This was taken just after the new year, at the start of 2020. And for those of you who do know the constellation Orion, you'll recognize the 2 stars in the top of the image comprising the shoulders of the hunter, the belt going across, the 3 stars there, the sword pointing down, and then the 2 stars at the bottom pointing to the tunic. This is quite a famous constellation, and I gaze at it whenever I get the chance. Will Gatter took a number of images in the early weeks of 2020. And you may get a sense that there's something a bit different between these 2 images. I think these images were taken in Dartmoor, somewhere fairly dark. few weeks later, he took another image. And I wonder if the transfer function of the various projection software is up to it, whether you get a sense that that orange-red star towards the top left is maybe a little bit different in the left image from what it is on the right image. This right image is rather harder to discern because it was taken where there was greater light pollution, I believe, in one of our cities. If I now show a zoom in that Wilgata prepared just of that star in the top left, whose name is Betelgeuse, by the way, and if I show you a movie based on this, then I hope you'll get a sense that while the other stars in the background remain very constant in brightness, Betelgeuse itself is going from bright to not so bright to fainter. The fact that the background light is brighter on the third image is a consequence of light pollution, which is a great hindrance of optical astronomy. So at the start of the year, many people were rather fascinated. How could this famous star in Orion, the wonderful orange-red Betelgeuse, how could it be going so dim? How could it be fainting? What on earth was going on? Excitement began to build. Some people wondered whether Betelgeuse was about to undergo a supernova explosion, and that would have been pretty exciting had it happened. It is likely that one day Betelgeuse will go into supernova, but possibly not for another 10,000 years. We'll have to wait and see, or at least wait. So why did the fainting of Betelgeuse happen? Why did it go so faint? The most likely explanation seems to be that this star spat off a lot of hot gas. Now, stars can do this from time to time, and our own sun is no exception. From time to time, bits of the plasma in a star are just spat out as that matter boils off and is ejected and launched into outer space. What happens to that hot gas once it's launched from the star? Well, that hot gas will cool as it goes into outer space and as it expands. And when matter cools, it can condense and coagulate into what we call dust. Dust is the word that astronomers use when they mean soot, i.e. black stuff that absorbs light and attenuates light. So if that process has happened, a whole lot of hot gas, hot plasma, has been ejected, and then it's cooled and it's condensed into soot along the line of sight to Earth, you will absorb the light. You will have attenuated the light. And that will cause the star to appear dim. And so that's the current best explanation for why Betelgeuse went so faint in the first part of 2020. It does oscillate around quite a lot, and so it's true to say that this object is still being studied in great detail by telescopes around the world. We don't know for sure what it's going to do next. Now, I mentioned that the third of these images, this one here, goes quite bright. It's got a bright background, and that's because of terrestrial light. I don't know where the third image was taken, but I feel sure there would be lights from nearby shops or residential houses or street lamps, something of that sort, making it much harder to see the faintest and finest stars that are possible in the darker images. So I want now to dwell on the fact of the question of how can we see the night sky? It really matters that you look somewhere where it's dark, somewhere where you haven't got pollution from street lamps, from houses and from shops and school buildings and so on and so forth. If you're looking for something of a hibernation project, you might like to get familiar with everything that has been curated on this website by the Commission for Dark Skies. They present a compelling case of why it's important to keep the skies dark for astronomy. That matters greatly to me as a professional astronomer and also for everyone else who cares about being able to see the sky clearly. The night sky is an area of special scientific interest, an area of outstanding natural beauty, and indeed it is if you can actually see it and it's not overwhelmed by terrestrial light. but light is not only important, or the absence of light is not only important for astronomers. Light pollution confuses cute furry mammals, insects, and bird life. And so besides the astronomical reasons for which minimizing light pollution is important, we know many studies have shown that both humans and animals sleep much more deeply, which is important for good health, when it's properly dark. There's an organization in Canada who have collected together a different symptom of the perils of light pollution from cities at night. The organization called FLAP, this is their logo here, which I always find very disconcerting because birds should not be that way up. But what FLAP has done is to collect together all the dead birds that have been killed by flying into illuminated buildings in Toronto at night. And they've laid them all out here. These are the cadavers of all the dead birds that flew into illuminated buildings at night. Artificial light from buildings and cityscapes endangers birds. Many species of birds migrate at night using light from the moon and the stars and even the setting sun to navigate. But the bright lights of our urban areas confuse these birds and pull them off course, out of their way. And so actually it's thought to be millions of birds that are killed annually on migration when they become disoriented and exhausted, circling and flying into brightly lit structures. There are lots of reasons why it's a good idea to minimize light pollution, so I do commend the Commission for Dark Skies to you. But back to Orion, back to what we can see in our night skies in the coming months. So this is the sort of image that can be seen with or taken with a digital camera, at least if you've got it on a very stationary support, such as a tripod. If you live somewhere really dark, in the outback in Australia, then you can see in this same direction in the sky a much deeper picture. This is actually taken with a small telescope. And you can see, if I go backwards and forwards, the same stars of the Orion constellation are there. But because the constellation of Orion is spread-eagled across the plane of our galaxy, when you are somewhere dark, you see vastly more than you would have expected from a relatively light-polluted sky. I wonder if you can see in the region of Orion's sword a rather bright nebula, which I'm indicating with this blue arrow here. This particular nebula is a very famous one. It's sometimes called the Orion Nebula because of its location. It's sometimes called Messier 42, the 42nd object in Charles Messier's collection. It's been studied for many years and admired and cherished for many years. One of the very early people to study it in great detail was John Herschel, son of William Herschel. And this is a drawing that he made of this particular region in the sky, the Orion Nebula, referring to an eyepiece which was far from the pristine optical quality that's available to us today, and patiently sketched the stars that he could see, those are the dots, and the extended plumage, or I should say nebula, the gas that's radiating because of the light coming from those hot stars. This is actually an inverted image. He would have sketched with a pencil or something on white paper, but I think it's a bit clearer to see in this very helpfully inverted image, which was described in an article in Sky and Telescope a few years back. It may seem to you that dwelling on and admiring a drawing of the night sky is perhaps a little archaic and belonging to yesteryear. Not a bit of it. Let me show you a modern day drawing of this exact same region in the night sky. This beautiful image, which surely is a labor of love, was drawn by Howard Banich in the United States. And the exquisite attention to detail here is something I am in awe of. You can see in great detail some of the details and structures in this beautiful nebula that is illuminated by the stars within. I think it's a safe bet to assume that Howard Banach has rather better optical quality eyepieces than were available to John Herschel. But there's no getting away from the fact that the hours and the dedication and the attentive eyes he must have used to create this beautiful image are truly breathtaking. I'm now going to show you the same image, but in a multicolour format. And I hope that that, again, reproduces reasonably clearly by the time it gets from my computer to yours. I want to draw your attention to something that tells me of the attention to detail that Howard Banach showed in producing this image. I'm going to focus on the stars at the very centre. These are often known as the trapezium stars on account of the four bright ones form the shape of a trapezium. I hope you might be able to see that just outside these four bright stars and a few fainter ones that are nearby, it's as though, on this drawing, they're sitting in a slightly dark halo. That is the signature of an accurate drawing by a human. Why do I draw attention to that? Well, there's an interesting detail here. Those stars stand out against a dark background. But if I now show you an image of this same nebula taken with a telescope, and this one I'm showing you here is taken at the Global Jetwatch School Observatory in India that I described to you in my third lecture, the one that was entitled The End of Matter, just over a year ago. You can see the very bright region where those trapezium stars are. If I zoom in even closer, using a slightly different camera system, then you can see there is no evidence of that dark halo around the stars that were faithfully reproduced in Howard Banach's drawing and also in the drawing centuries earlier by John Herschel. What's that all about? Did they make a mistake? On the contrary, they both drew, Howard Banach and John Herschel, they both drew exactly what they saw. The important detail here is that when you look at very bright things, when human eyes connected to human brains look at very bright things, our eyes and our brains are overwhelmed by the bright signal from the stars being looked at. And so no light is detected from their immediate surroundings. Those drawings faithfully show what the human observer sees. But in reality, there is no dark pool around them. There is no dark halo around them, just radiating light, reflecting, in some sense, re-radiating the light from those young, new, hot stars. The Orion Nebula is a region of ongoing star formation in our universe. And while I have never had the time or the patience, and indeed probably I lack the drawing ability to do anything approaching what John Herschel or Howard Banach have done, I'm in awe of it, and I greatly admire that important detail that authenticates the way their human eyes work and being faithful to the data as they observe it, at the same time as being able to understand and reconstruct the astrophysical reality. It is fascinating how eyes work. It is fascinating how, for all their imperfections, their non-linear responses, and their vulnerability to misinterpretation by the brain, it is nonetheless fascinating the contribution that eyes can make to astronomical endeavours. I'm showing you here an image which I showed in my lecture in May, the one on perceptions, expectations and discoveries, of Messier 1, number 1 in the catalogue of Charles Messier. You definitely need a telescope for this particular object, by the way. This particular object came into existence a millennium ago. It was observed by the Chinese in 1054 as a supernova explosion that then ejected into outer space all this debris that we now observe as the Crab Nebula. This particular object is a favourite to look at if you've got a reasonably good-sized telescope. This particular object, the Crab Nebula, Messier 1, was being observed at the McDonald Observatory one night in 1957 when there was a public open night for the telescope that they had there, which is 82 inches in diameter. It's about 2 meters in diameter, longer than I can stretch. This particular telescope was focused on the Crab Nebula that I had in my previous slide. And I'm showing here a picture of Jocelyn Bell Burnell because she told me a very interesting story about something that happened on that open night, that observing night in 1957. She relayed to me a story told by Elliot Moore of how the public stepped up in turn to take their turn at looking through the eyepiece on this huge telescope at this particular object, the Crab Nebula. In particular, Minkowski's star within it. So one member of the public stepped up to the telescope and said to the night assistant, "That star is flashing." So the night assistant started to explain to that member of the public about scintillation. Scintillation is something we're probably all fairly familiar with. Another name for it is twinkling. When we look out and see twinkling in the night sky, or scintillation in the night sky, that's the phenomenon that was giving rise to the blurriness and the bouncing around and the bobbing in my movie sequence of Mars at the start of this lecture. Twinkling is kind of all very gorgeous when you're looking at the night sky, but it's not so great if you want to focus in great detail on one particular object. So as the night assistant, the telescope operator at this public open night at the McDonald Observatory was about to launch forth into an explanation of scintillation and twinkling to this member of the public who was saying, "I can see that star flashing," she politely pointed out to him that she knew all about scintillation because she was a pilot and was used to flying by night. This is rather amazing, by the way, that in 1957, a young woman should hold a pilot's license. So this member of the public flies at night, knows the night sky, because what else is there to do in a dark cockpit in a plane by night? And so she knows about scintillation. And she's very insistent that what she sees through the eyepiece attached to this huge collecting area of an 82-inch telescope, she is insistent that that star is flashing. Why have I drawn your attention to the fact that it was Jocelyn Bell Burnell who told me this story? That flashing star turned out to be the Crab pulsar. So human eyes can see ahead of their time. If they're very clear and very honest about what they see, then that can lead us to remarkable insights into what's going on in the night sky. So it's in the center of this Crab Nebula, in the center of Messier 1, that resides the Crab pulsar, which Jocelyn later discovered some years after this young woman at that public open night at the McDonald Observatory reported it to be flashing. Well, it is certainly true to say that our eyes, if appropriately trained and well adjusted to seeing at night, can see amazing things. Back now to John Herschel and a different, very beautiful nebula in the night sky. This is possibly one of my favorites, not so much in this early version, because again, in the times when John Herschel was observing, the optical quality of his eyepieces and indeed telescopes were really not that great relative to modern standards. This is really an object to see in all its beauty with a telescope. And I think this really is one of my favorite nebulae in the whole sky. Messier 8, again, gas surrounding a region of current ongoing star formation being illuminated in all its glorious swirls. This is one just with a very slightly different colour scheme taken from my Global Jetwatch School Observatory in Chile. So telescopes and eyes together can help us form a really good picture of what's going on in the night sky. What are the analogies, I wonder, between how telescopes see, or cameras on telescopes see, and how eyes see? What are those analogies, and how does this all fit together? Well, this movie was prepared with the help of Lucy Wright, and I hope it shows very clearly, or will show when I start playing, how the eye and the brain function compared with how a telescope and a camera function. So let's watch this movie now, and you can see that light obviously passes from the apple or whatever through the cornea, through the aperture formed by the iris, being focused a little bit by the lens onto the back detector of the eye that I mentioned earlier, the retina, and then that light signal goes to the brain and gets interpreted there. Whereas for a telescope and a camera, let's say that we're looking at the moon, we've got rays of light passing onto the primary mirror, onto the secondary mirror, being focused onto the detector, in this case a camera, controlled by, stored by a computer. How much the eye and the aperture actually see depends on the size of the aperture. The more your pupil is opened, the more light you will collect. That's why you need to dark adapt at night. For a telescope, you can't change the aperture, you can't change the collecting area. You can buy or borrow or look at someone else's larger telescope, but really your collecting area is fairly fixed. But there's one key advantage that using a telescope and a camera system has compared with using the eye. And that's the following. With a camera, you can expose for a long time. So when light impinges on the eye and lands on the back of the retina, typically it's the light averaged over 1/10 of 1 second or 2/10 of 1 second that gets collected and then interpreted as an image by the eye. Whereas with a camera, you can set the exposure time to quite a range of different values. So the image that I showed you a bit earlier of the comet with the meteor nipping nearby it, that exposure time was 4 seconds. With a camera, I've taken exposures which have been an hour long in length, and of course seen very, very faintly, very, very deeply into the night sky. There's basically no chance of saying to your eye, look, come on, integrate for longer than 1/10 of a second or two, collect more light. If you want to increase the exposure time and collect more light to see more deeply, it's time to turn to a camera. But you can assist your eyes in different ways. One way of collecting more light so that you get more light landing on your retina is to use an eyepiece and a telescope, of course, or the very best way, if you're just getting started in observing the night sky with your eyes, is to use a pair of binoculars. Brains typically work best when they're using light from more than one eye. 2 specifically is quite a good number of eyes. Binoculars collect that bit more light, they focus it, and we then get a stronger signal of fainter targets in the night sky. So there are important differences between observing the night sky with our eyes, albeit with some kind of optical assistance like binoculars, and using a telescope. But it is important to emphasize that even this bottom route, using a telescope, using a camera, those camera images nonetheless still get interpreted by the brain. This arrow here says to the computer, but who operates the computer? That's a human. And so interpretation of astronomical data is a really big deal and is something else that one could in principle bring non-linear or prejudicial perspectives too. But the big difference between using the eye and using the telescope, as I've indicated, is collecting area. So I'm going to show you something of a self-portrait right now. This is taking a photograph with my digital camera, looking at the primary mirror of my telescope at the school observatory, part of the Global Jet Watch network in Chile. So the diameter of my retina is a few millimeters, and that can see so far at night. The diameter of the aperture of that particular camera lens is a few centimeters, so that can collect more light, and I can see more deeply into space than I can just with my eyes. But the diameter of this particular primary mirror is 0.5 meter. And so that's why we can see that very beautiful nebula of Messier 8 that I showed you a few slides ago. Collecting area really does matter for astronomy. Size matters when you're talking about the size of the light bucket with which you are collecting light signals from different parts of the galaxy or beyond. Let me talk about something a little different that we might hope to see in the night sky in the coming weeks and months. So I started this particular lecture with a conjunction of Mercury and Jupiter and the Moon. A conjunction, again, is where two planets or other known stars come very, very close together in the night sky. They're only close together in an angular sense. They're not close together in a radial sense, but close together as they appear to us on the sky is a very beautiful sight indeed, as you saw from the first astronomical image that I showed you in this slide. I want to talk about a very special kind of conjunction now. This is one that astronomers refer to as a great conjunction. So a great conjunction is specifically where the two planets that come close together are Jupiter and Saturn, the most majestic of the planets in our solar system. When they form a conjunction, it's called a great conjunction. Now, the last time that we had a great conjunction visible from Earth was in 1623. In 1623, Gresham College was still only on its third professor of astronomy. 1623 is quite a long time ago. The last time Jupiter and Saturn came close together was 1623, a few centuries ago. The next time it's going to happen is in just a few weeks' time. So what I would suggest is that if you have a good view to a southwest horizon, you start looking out for where Jupiter is in the night sky and where Saturn is in the night sky. Don't worry if you haven't yet practiced and mastered the dark adaptation techniques or the averted vision techniques that I referred to earlier in my talk. Jupiter and Saturn are super bright. They are in your southwest horizon. And if you watch them whenever you've got a clear night, in the coming few weeks, you will see them get closer and closer and closer together. Closest approach will be at about 6 p.m. UK time on about 6 p.m. on the 21st of December. So if you're looking for a hibernation project during lockdown winter, I really recommend looking at the night sky with your eyes. Let me give a health warning that warm coats and warm boots have been known to be an asset when looking at the night sky from this particular part of the world. If you want to look at this great conjunction on the 21st of December, start looking now while you get used to what your eyes are seeing. Seeing and understanding what is in the night sky takes practice and takes training. And if you want to have a context for the special event that's happening on the 21st of December, less than 2 months from now, the last example of which was in 1623, start looking now and watch them getting closer and closer together. This particular image shows Jupiter over there, Saturn there, and a couple of bright stars. So if you see that rhombus gradually forming, and you may well find it easier with binoculars or something, Jupiter and Saturn will be only 1/10 of a degree apart on the 21st of December. Then if you can see it, you're in for a treat. But prepare yourself for it by watching them come close together. What else can human eyes do in terms of astronomy? Believe it or not, what human eyes see in the night sky can contribute to research in professional astronomy. Let me show you how this happens with a few slides kindly given to me by Stella Kafka, who is the director of the AAVSO, the Amateur Astronomers Virtual Observatory. So what Stella has been a great advocate for, and a very successful advocate for, is people who look at a particular group of stars flagged up on their website as being important for professional astronomers on a particular night, and to capture and record faithfully and honestly what they see. So the way it goes is the following. Imagine that the star that's delineated by those two horizontal lines has newly appeared, like a nova explosion. What we in the world of professional astronomy really want to know is, how is that changing? In what ways is it changing, and how fast is it changing? Now, the problem is, not all telescopes, far from it, are available to observe changing phenomena in the night sky. That's why I instigated the Global Jet Watch telescopes. But even then, telescopes, if they're pointing at a different phenomena in the night sky, can't necessarily stop what they're doing and look at a newly appeared star in the night sky. So what Stella Kafka and the AAVSO do is they ask people, they encourage people to watch what's happening and to make a comparison of the newly appeared star with nearby stars that are unchanging and whose brightness is known and calibratable. So you can answer questions like, is the newly appeared star delineated by the horizontal lines brighter or fainter than star 91? Today, the 10th of June in this example, it's quite a bit brighter than 91. Is it brighter than 85? Yes, it is. Is it brighter than number 75? Yes, it is. Is it brighter than number 64? Yes, it is. Brighter than 61? No. So you have then bounded the brightness of the new star between number 64 and number 61. You do the same game a few nights later. You do the same game, even if it's cloudy, by the way. You can still do this same kind of analysis, because as long as you haven't got overly granular cloud, then the relative brightnesses of the stars will remain the same relative to one another. On another date, you might see the brightness of the star change even further. And you can capture this and then plot it. So a plot in astronomy against time on the horizontal axis and with brightness, doesn't matter what the units are, they're relative to the nearby stars. If you plot the brightness, that is something that is known as a light curve, a time series of brightness data for a particular star in the night sky. If you keep going with that, and if you're joined by friends all around the world who are either just using their eyes together with binoculars, or maybe with a digital camera, or maybe they're lucky enough with a telescope, collectively, lots of points can be plotted to get the desired light curve. Let me explain to you why this data collection, this light gathering and light comparison game or exercise is so valuable. I'm going to show you now a light curve of the brightness of a newly exploded star called a nova, which went off in Sagittarius in 2015. As with all light curves, we've got time on the bottom axis. The units here are days since detonation. And then I've got a particular axis which represents the brightness of stars. I don't know about you, but I think that's a pretty scruffy light curve, and it's quite hard to understand what's going on. These are the only light curve data that were available for telescopes in the first weeks after this particular nova exploded. However, if I now overlay on this plot the data from human observers all over the world, collected thanks to the work of the AAVSO, you can see much more clearly the zigzags and up and down changes in the brightness of this particular nova explosion, which is exactly what we, as professional astronomers studying nova explosions, really, really want. As time went on, this was in sort of late spring, early summer of 2015, things evolved really quite dramatically. There was a sudden drop in the brightness, and which is basically when a whole lot of matter was thrown off the star, just as in Betelgeuse's dimming that I referred to earlier in my talk. The brightness of the star plummeted. It became a whole lot fainter. You can see the dip there just after 100 days, and then it gradually recovers. It was absolutely brilliant. It is absolutely brilliant to have the complementary data from the AAVSO all the way around the world, filling in the gaps and filling in the dots. There's more scatter on these measurements, more uncertainty in them, because human eyes are not perfect, and all that sort of thing. But that still means they are scientifically useful to us. So hooray for the AAVSO. As one of my graduate students, Dominic McLaughlin, and I are studying this particular nova explosion in Sagittarius, looking at all sorts of changes in the spectra of this particular star as it evolved. This is very early stage. As these signatures move around and go up and down, is massively helpful to have those filled-in light curves from friends and supporters around the world. So again, if you're looking for a hibernation project, I recommend that during this lockdown winter, you take a look at the website of the AAVSO. I hope this has given you a sense of everything that human eyes can see, and that despite the imperfections of human sight, despite the fact that human eyes are non-linear in their response to the light that lands on our retinas, despite all of that, observations, attention to detail of what's going on in the night sky can still be fantastically scientifically useful if we have faithfully attentive eyes. And that's the end of my lecture. Thank you.
Thank you very much, Professor Blundell, for a really fascinating lecture. I do have a couple of questions from our online audience. A couple of them deal with equipment. One of our audience members is interested in the size of telescope used for the video of Mars.
So the telescope that was used for the particular video of Mars was a relatively large one by amateur standards. It was about 14 inches in diameter. But I'd like to hasten to add, you can get similar images that give you the same qualitative features of the different colored surface across Mars and of its rotation, even with a good digital camera and a good lens, if you've got a tripod. I sometimes think that the most important equipment for doing these kind of observations isn't necessarily the fancy optics, but it's the stability of your tripod and the warmth of your coat and your boots. I hope that helps.
How are machines able to take pictures on Mars while dealing with external factors, for example, dust, radiation, etc.?
That's a very good question, and the answer is it's not easy. So any images that are taken whether they're with human eyes or with cameras and telescopes on the ground or in satellites, for any of those data that are being captured and recorded, it's crucially important that a process of calibration takes place. In that little game of the AAVSO that I was illustrating, where in turn you say, is this new exciting star brighter than this star, fainter than this star today, compared with yesterday, that process is actually called photometric calibration. Calibration is the means by which we can take imperfect, flawed, non-linear observations of what we see in the sky and turn them into scientifically useful data. But it's absolutely fair to say that even for cameras on a satellite, cameras on a telescope, calibration is absolutely a crucially important process. In the case of dust, dust can re-radiate infrared light, and that's something that we absolutely seek to subtract out very, very carefully from the images that we study. So too are things like cosmic rays, which will be the subject of a lecture that I'll be giving in the new year. Calibration is crucial, whatever you're doing, but your understanding of how you need to do that calibration, whether you're looking by eye or looking with a telescope on the ground or with a satellite, that absolutely is something that's informed by experience and by the curiosity and the inquisitiveness of human nature.
Thank you. Does the lack of cratering on Mars compared to the Moon suggest that the cratering primarily occurred back when Mars had an atmosphere, before it lost its magnetic field? Surely today's atmosphere would not burn up the meteorites?
That's a very good question. There are certainly some craters on Mars, as I mentioned. Fewer than are on the Moon, more than are on the Earth. And I think exactly why there are few relative to the Moon, which, as I described in a previous Gresham lecture, are so numerous because the Moon basically doesn't have an atmosphere, so nothing burns up en route to going splat on the Moon's surface. That very much depends on the history of the evolution of Mars itself, the geological formation, as well as on the evolution of the atmosphere. So it's an interesting question, and I don't think it's entirely fully resolved as yet.
And one final question on equipment. Could you suggest optimal size/strength of binoculars for sky watching? I much prefer using 2 eyes to 1.
I absolutely agree with the sentiment that using 2 eyes is much preferable for astronomy because our brains have evolved to work with 2 eyes and get stereo vision. So absolutely do get some binoculars. Quite what you go for, I think, depends on your eyes and where you are going to be observing. If you're observing from the UK, then maybe what you want is a little bit different from if you're going to be observing from the bush in South Africa or Botswana or somewhere. So what I would do is read around on the websites of Sky and Telescope or Sky at Night or Astronomy Now and look into the various pros and cons and relative merits. It doesn't need to cost you a fortune to get a really super pair of binoculars that will massively enhance your night sky observing experience. Don't rush into it though. I'd read around it first and make sure you're making a really good choice for you in the context and location that you're in.
That's wonderful. Thank you again for a great lecture and for your willingness to answer questions as well. Thank you all for attending this afternoon. I'd like to encourage you to return for Professor Blundell's next lecture, which will be held on Wednesday, the 18th of November at 1 p.m. And that one is Cosmic Vision, Witnessing Fireworks. See you then.